In this video, we're going to look at curl and divergence, two different properties of vector fields. So let's look at the curl first. The curl of a vector field is defined to be the gradient of nothing. That's a little odd. We've always taken gradients of functions. We're finding the gradient just all by itself, crossed with the vector field. Now, you'll have to remember what a gradient is. Now, when we have found a gradient of a function, it's been partial derivatives of that function with respect to each variable. So if there was a gradient of f, we'd find a partial of f with respect to x, but in this case there's no f, it's not in there. Then we would take a partial of f, but it's not in there with respect to y, and same thing with z. We're just going to take a partial with respect to z, but we're not actually taking partials of any functions yet. This is just a gradient all by itself. All right, so this gradient right here is given by this formula, and we're going to cross that with the vector field. So I think this is easiest done with an example. So let's find the curl of the vector field, e to the z, and then sine of x, so sine of x plus y, z squared plus 2xy. Okay, so the curl is it's a cross product. So the curl of f, we have to find a cross product here. So we'll put I, j, and k in the first parts of it. Now we're crossing it with this function. So I'm going to put that, because it's last, I'm going to put it in the bottom. And I'm putting it before the vector field because I don't know how much space I need. So e to the z is the first component. Sine of x plus y is the second component. And z squared plus 2xy is the third component. I'm going to erase these guys and give myself a little bit more room here. All right, so there's j. There's k. And now in the second row, I need these partials of nothing. Partial with respect to x, partial with respect to y, and partial with respect to z. Okay, so now how this cross product works and how these partials of nothing works. So for the I component, we ignore that I column and we look at, for the j, we cross there and then we cross there. And what this says is we are going to take a partial derivative with respect to y of this function. So that's a partial with respect to y of this function, and then we're going to subtract the partial with respect to z of this function when those get multiplied. All right, so the partial of this function with respect to y is just going to be 2x. Minus the partial of this function with respect to z, well, there's no z in there, so it's 0. The negative, or the j component of a cross product is negative. We're going to ignore the j column, and we're going to take the partial with respect to x of this function, which would be 2y, minus the partial with respect to z of this function. There's a z in there. It is e to the z. For the k component, we're going to take the partial with respect to x of sine of x of y. So that has a sine of x in there. So cosine of x is the derivative there. Minus, so that's just a minus. There's no comma in there. So minus the partial with respect to y of e to the z. There's no y's in there. That's 0. And so our curl would be 2x negative 2y minus e to the z cosine of x, and that's it. That would be our curl. Now, what the curl does is it measures it measures how a fluid rotates. So we could say that a fluid rotates in the direction of the curl. In the direction of the curl. So if you're in a fluid, if there's no curl, so that means if the curl ends up being the vector 0, there are no whirlpools. I think that gives a pretty good kind of geometric description of what curl is. So if the curl is 0, there's no whirlpools. Otherwise, a fluid is going to be rotating in some way. So a few other Okay, so a few other facts about curl. Now, if F is conservative, and remember this means that the vector field would be equal to the gradient of some potential function. We looked at that before. So if F is conservative, this means that the curl is going to be 0. So then the curl, let's see if I can write with this pen. So this means that the curl of that vector field is equal to the 0 vector. All right, so if it's conservative, then the curl is 0. It's not necessarily true the other way around. If F is defined everywhere, so this means there can't be any divisions by 0, there can't be any square roots, there can't be any natural logs in there. So if F is defined everywhere and the curl is 0, and the curl is equal to the 0 vector, then F is conservative. And remember that what this does for us is if this is true, then we can apply the fundamental theorem of calculus, and we don't have to actually evaluate a line integral. We can just find a start point and an end point and plug in values. So this is kind of a nice fact, but these very specific things have to happen in order to kind of take that shortcut. All right. Okay, so that's it on curl. Let's talk about divergence for a minute. So the divergence of F it's denoted div of F. And the divergence is the gradient dotted with the vector field. So it's that gradient of nothing again, dotted with the vector field. And if you do this dot product, you are going to get the partial of P, which is the x component of the vector field, with respect to x, plus the partial of the y component with respect to y, plus the partial of the z component, which is r, with respect to c. So there's divergence. So if we go back to that same vector field that we had before, it was e to the z y plus the sine of x, and then z squared plus 2xy. And if we find the divergence of this vector field, we take the partial of the x component with respect to x. Well, there's no x in there. 0. The partial of the y component with respect to y, there's a y in there, numbered out in front is 1, so that would be 1. Plus the partial of the z component with respect to z, and there's a z in there, so derivative would be 2z. So the divergence of f is going to be 1 plus 2z. So curl is a scalar. I'm sorry, said that wrong. Curl is a vector. Divergence, you get a scalar function. And divergence measures the tendency of a fluid to diverge from a point. So this measures the tendency of a fluid to diverge from a point. So is the fluid moving towards that point, or is it moving away from that point? And that's kind of what the divergence would tell us. Okay, I think that's it. Now the next thing that we're going to do is look at some theorems where we can have possibly a simpler way to do line integrals and a simpler way to do surface integrals, so sort of some shortcuts, and they use the curl and divergence.